One of the rules in our proof system is the reductio ad absurdum rule, which says, given a finished subproof starting with the temporary supposition alpha and concluding absurdity, we can derive not alpha. This rule gives you a way to derive the negation of a formula. I'll go through two examples. So first, let's suppose that our aim is to use our proof system to show that the following reasoning is valid. R and not Q, not P and R, thus not P and not Q. The conclusion that we're aiming to derive is a conjunction, so it makes sense to try deriving each conjunct separately and then using conjunction introduction as our last step. Deriving the second conjunct not Q is easy, since not Q just appears as one of the conjuncts in the first premise. So the conjunction elimination rule allows us to derive not Q from that premise straight away. What about not P? There's no similarly straightforward way to derive not P, so it makes sense to try using the reductio rule to derive not P. The way that works is that at line 4, we say, well, let's suppose that P was true in addition to our premises. Because we're now going to consider what follows, not just from our premises alone, but what follows from our premises plus the extra assumption P, we create a new column of reasoning with P at the top of it. And the idea behind creating this new column of reasoning is that it gives us a really nice way to keep track of when we're working under the assumption that P is true in addition to our premises, and when we're working under the assumption that just our premises are true. As long as the things we're assuming to be true are our original premises plus P, then we'll stay in this new column. When we want to go back to assuming simply that our premises are true, which we'll inevitably want to do because we ultimately want to prove that the conclusion not P and not Q follows from our premises alone, not that it follows from our premises plus some extra assumption, we'll end this new column and go back to the original column. So here we are, assuming that our original premises plus P are all true. Our goal is now to show that if P were true in addition to our premises, then that would lead to absurdity. Because if our original premises plus P lead to absurdity, then that means that if those premises and P were all true, then absurdity would be true, which can't happen. So if our premises together with P lead to absurdity, then that means that it can't be that our premises and P are all true together. But if they cannot all be true together, then anytime our premises are true, P must be false. So anytime our premises are true, the negation of P must also be true. So if we show that our premises plus P lead to absurdity, then we can end the new column of reasoning and write the negation of P back in our original column of reasoning. Because by showing that our premises plus P lead to absurdity, we'll have shown that our premises alone entail the negation of P. Now, how do we show that our premises plus P lead to absurdity? We have to show that they lead to an explicit contradiction, that they lead to both a formula and its negation. So how do we show that they lead to an explicit contradiction? Well, our premises include the negation of the conjunction P and R. So if from our premises plus P we can derive the conjunction P and R, that will mean that from our premises plus P we can derive an explicit contradiction, namely P and R and not P and R. To derive the conjunction P and R from our premises plus P, we just need to derive R, because then conjunction introduction will allow us to derive P and R. And we can derive R straight from the first premise using conjunction elimination. Now, having shown that our premises plus P lead to absurdity, we're entitled to conclude that the negation of P follows from our premises alone, so we end the new column of reasoning. We stop assuming that P is true in addition to our premises, and we write not P back in the original column of reasoning. As our official justification for line 8, we appeal to the reductio ad absurdum rule and the subproof that starts at line 4 with the temporary supposition P and ends at line 7 with absurdity. Finally, having derived both not P and not Q separately, we finish the proof by using conjunction introduction to derive not P and not Q. Now, for a second example, let's suppose that we want to use our proof system to show that this reasoning is valid. Not P and Q, Q, thus P. How can we derive the conclusion from the premises? Note that if not P were true in addition to our premises, then both not P and Q would be true, and that would contradict the first premise, which denies that both not P and Q are true. So if we were to suppose that not P is true in addition to our premises, that would generate a contradiction and hence lead to absurdity, which means that we could use the reductio rule to conclude that not P follows from our premises alone, and then from not P we're allowed to derive P via the double negation rule. So that will be the overall idea of our proof. Filling out the details, once we've temporarily supposed not P to be true in addition to our premises, we derive the conjunction of not P and Q from lines 3 and 2, from which we can then derive absurdity in combination with line 1. Then we stop supposing that not P is true in addition to our premises, so we close the subproof with not P at the top of it, and we write not P back in the original column of reasoning, citing RAA and lines 3 to 5. Finally, we derive P from not P using the double negation rule. This proof illustrates an important strategy. On the face of it, the reductio ad absurdum rule is a rule that you turn to when you want to derive a formula of the form not alpha. So if you want to derive not P, for example, you might try temporarily assuming P and then deriving absurdity. Or if you want to derive not R and Q, you might try temporarily assuming R and Q and then deriving absurdity, and so on. However, sometimes it makes sense to use the reductio rule even when your ultimate goal is not to derive a formula of the form not alpha. You might use it as we just did when what you're ultimately trying to derive is P or Q and R, or some other formula that does not have a negation out front. And that's because a formula is always derivable from its double negation. So no matter what formula you're ultimately trying to derive, you can always try temporarily assuming its negation and then deriving absurdity, which will get you the double negation of your ultimate goal, which then gets you to your ultimate goal by an application of the double negation rule. Being aware of this proof strategy is important because it is sometimes necessary to use it. For instance, there's no other way to do the proof that we just did. However, once people see that this strategy is available, they sometimes overuse it. As soon as they get stuck in a proof, they just try assuming the negation of what they want to prove with hopes of that leading to a contradiction. But that strategy won't always help. So it's best to use it as a kind of last resort when you've truly exhausted all other options.